Okay, good afternoon. I've just noticed that my lecture notes say midterm 2 is this week, but that's wrong. I have to correct the notes. That's left over from the previous arrangement of weeks. Midterm 2 is a week from this Wednesday, October 15th, not 2 days from now, at 7 o'clock, and sadly it's in 155 Dwinell. So we'll talk more about the midterm later. It's about half written, I would say, at this point. It used to be all the way written, but we rejected a bunch of questions after trying it out on the TAs. So what we're doing this week is a big shift in focus. So we've been going now for almost 2 months, and through all that time concentrating on functional programming, which is seeing what mileage we get out of the idea that every procedure we write is a function that gives the same answer for the same arguments regardless of the past history of the computation. So we have no sense of history when we're doing functional programming. And now we're going to shift into the opposite way of thinking, where we do care about the history of the computation. And we'll see that that sort of makes things messier, because there are a lot of ways that procedures can interact badly with each other. And one of the things that we're going to try to do to fix that is another programming paradigm, which I'm sure you've heard of, called object-oriented programming. The really interesting story for us about object-oriented programming is the story you'll see next week, which is that the scheme language, the same language that you've already learned all of, pretty much, one exception, I think, can do object-oriented programming. The one exception is you haven't learned how to change something yet, but you will today. We don't have to have scheme plus plus. We don't have to invent special notations and special vocabulary for doing object-oriented programming. Nevertheless, that we are going to do that this week. So we're going to use an extension to scheme that provides object-oriented capabilities and that more or less uses the vocabulary that other people use to talk about the different aspects of object-oriented programming. So the point of all this is for you to see how what we're doing here can fit in with the world of what those other people are doing. So we're looking at the above-the-line view of object-oriented programming, and we're leaving until next week what capabilities really make it work under the rug. But of course, as you can imagine, I'll just give you a hint, there's some lambda involved. So this is a new kind of abstraction diagram that has this funny dotted line across here. And what that means is that between this level and this level, there's no computer programming going on. There are no procedures that implement the abstraction. This top-level abstraction is something that exists only in your head. And the thing that exists in your head is a metaphor, which is inside the computer, there are multiple independent, intelligent agents. Okay? Multiple means there can be a lot of them. Independent means they all independently, each independently does something or other. This can do its thing, that one can do its thing over there. Although they interact, if one of them bumps into another one or something, they can communicate between each other. But they each have their own programs. And they're intelligent. Each one knows how to do things. So an object, from one point of view, is a data structure, just like the data structures we've been making for the last month. But this is an intelligent data structure that knows how to carry out certain activities. So you can see that it's going to draw on the idea of message passing that we learned last week. Remember, what message passing means is that given that table of operators and operands, we draw a circle around a horizontal line in that table, which is an operand type. and we say we're going to put all the intelligence about how this kind of object does things in the object. So that's why we have smart data structures, which is what objects are, instead of the traditional sort of passive data structures that you have to write programs elsewhere to do things with. So message passing is the first idea that we're going to need to make multiple independent intelligent agents work. That's where the independence and the intelligence comes from. We're also going to want something called local state, which means we want each object, each thing in our system, to be able to remember stuff, independent of all the other objects. And we're going to see how that works mainly next week. We'll see how to use it this week, but how it works we'll understand better next week. And then finally, inheritance, which helps solve the problem that somebody asked about last time, which is if you have that table with types and operators, sometimes a lot of different types have some similarities, and so you're going to have different cells in that table that basically have the same behavior. They use the same method, the same algorithm for responding to some operator. And what we're going to see is that objects can say, well, I want to do this and this and this in my special way, but everything else I want to do the same way that other object does. And that's what inheritance is all about. So that's the week. There are three main things that implement this abstraction. We invent a new special form called define class for making a class of objects. And we have, so this is the constructor, not for objects, but for types of objects, for object classes. A class is a type of object. So that's define class. Instantiate, you can look at as a selector for classes, but also the constructor for instances. So given a class, if you instantiate that class, you are making a particular object of that type. So it's the difference between, rational numbers and 2/3. And then ask is how you send messages to objects. If you want an object to do something, you call ask with the object and the message you want to send. And then it does whatever it does. Okay. In order to use all this, you have to load it into Scheme. It's not built in for you. So here's what you do. You load ~CS61a/lib/obj.scum. That's our implementation. Basically, it's our implementation of define class. Although, the other ones are in there too. Most of it has to do with making define class work. Okay, on to the demo. So the first example doesn't do anything that you couldn't do before, but it just shows how to do something you've done before in this define class notation. So we're going to make a complex number, and to make one you have to specify its real part and its imaginary part. And the things it knows how to do are magnitude and angle. Those are the methods that it has. So it responds to messages, magnitude, and angle. So let me show you that working. If I say define complex number 1 to be instantiate complex. Note it's not quote complex. It's complex, which is a class. That's a kind of thing. Real part 3, imaginary part 4. I can now say ask CN1 quote magnitude. You get the answer 5, or ask CN1 quote angle and get not quite a radian. Okay? So So what we've learned about define class is that inside it you can have method clauses. A define class, the way a define class works, the first argument sort of to define class, it looks like a define that's defining a procedure, so the procedure name would be complex and the parameters, real part, and imaginary part. It's sort of like that. This is telling us that we're defining a class complex. So we should let me have a little vocabulary list. So we know about class, which is a kind of object, an instance, which is a particular object of that class. We're using the word clause to describe the stuff that's inside the body of a defined class. So a defined class is sort of like a cond in that it has a lot of clauses in it. In that top line, complex is the class name, and the other things are instantiation variables. So what's an instantiation variable? It means every time we make an instance, that instance has associated with it something called real part and something called imaginary part that have values. In our object system, this is not true of every object-oriented language, but in our system, to make things easy and less sort of typing for you guys, every instantiation variable and every object variable, we'll see later, there are other kinds too, has a method to tell you its value. So I can also say, ask cn1, quote, real part, and it'll tell me 3. So there's an instantiation variable called real part that has a 3 in it, and there's also a message, real part, that has associated with it automatically a method that looks in that variable and tells you its value. Okay? Questions so far? Yeah. Right. The question is there any way to have private instance variables? In that language you used last year, there's a big emphasis on objects keeping secrets from other objects. And the reason for this, and it's not a ridiculous reason, is to avoid bugs. That to make it so that if different kinds of objects are going to share information, going to be able to look at each other's stuff, you have to say so explicitly. So you say these variables are private and those other variables are public, meaning everybody can look at them. We haven't done that in this system because basically for debugging it's just a lot easier if you can always see what's in all the variables. Yeah? What if you want to put methods outside the class definition? You can't, not in this system. Okay. This system was designed around the idea of being good enough to get Project 3 done and being simple enough for you guys to understand through and through. So yeah, there are a lot more things, a lot more complexities that you can add to the idea of object-oriented programming. But I think for you to see what object-oriented programming means, it's easiest if we don't make things as complicated as possible, but instead make them as simple as possible. Okay, so that's instantiation variables. And then a method, basically the syntax of method is exactly the syntax of lambda, except that, I'm sorry, is the syntax of define for defining a procedure. So if that method, if the word method up here said define instead, we would be defining a procedure named magnitude that has square root of blah, blah, blah as its body. And when you called magnitude, you would evaluate that expression. And that essentially is what it means, although we'll see later that it doesn't actually define a procedure called magnitude, because that magnitude is the token, the word, the sort of password kind of, that's passed into the object to say, please do this for me. So it's really just a word that's stored someplace with this method associated with it. But the notation is just what the notation would be if we were defining a procedure named magnitude that's local to the class. And we chose that syntax because, it reminds you of things you already know. Okay, so we can make as many complex numbers as we want, and we can ask them all their magnitudes and their angles and the real parts and imaginary parts. So let me go on to the next example where we can do something new. And the new thing we can do is have counters. So I'm going to make a couple of counters. I'm going to define C1 to be instantiate counter. And we're going to define C2 to be instantiate counter. And now I'm going to say ask C1, quote, next. That's not what I meant. I get 1, 2, 3. So already you can tell that we're not doing functional programming anymore, right? Because I called ask with the same arguments, and I got a different value each time. And I can count this up as high as I want. So now it's at 4. Now let me ask C2 next. C2 starts at 1. And now if I go back to C1, which was 4 last time, it's 5. So each counter independently remembers what it was up to. So this is the paradigmatic example of local state. And how does it work? Well, there's two things you have to know about. One is there's a kind of clause called instance vars. Instance vars is kind of like a let, except it doesn't have a body. The body of instance vars is the whole define class, essentially. Okay? But the notation is the same. It's like what the sub-expressions of an instance vars clause are like bindings in a let, name and an expression for the value. In this case, there's only one instance variable. It's called count. And the expression that gives it its value is very simple. It's 0. But it could be as complicated as you want. You could compute it, some function in here, and it would be fine. So every time we make an instance, part of making the instance is sort of giving it a pocket labeled count and putting a 0 in that pocket. So the difference between instance variables and instantiation variables, I guess I should write instance variable here. An instantiation variable is an instance variable in the sense that it belongs to the instance. The difference is, where does its initial value come from? For an instantiation variable, the user specifies a value while instantiating the object. For an instance variable, the class definition specifies the value. So every instance starts out with the same value. In this case, every counter starts out with a count that's 0. So notice, by the way, that count is not the name of anything global. Oh, yes, it is, because there's a procedure called count. Never mind. But that count has nothing to do with the counts of these objects. The procedure count counts, the number of words in a sentence or the number of letters in a word. Maybe I should have called count something else, but the count for each counter is hidden within it. You can't get to see it globally. Although, of course, I can ask C1, quote, count, instead of saying next, and I get the same number I'm already up to. So ask C1 count. There. Gets the same answer. All right? Ask C2 count is 2. Right? The other thing in here that's new is set bang, which I'm going to write down somewhere else. So this is a new piece of scheme, real scheme, not part of the object system. Set bang, the exclamation point is pronounced bang, says it's sort of like define, the kind of define that doesn't abbreviate a lambda. So if I say, define pi, 3.14, etc., it's set bang, variable name, expression to provide a new value. So this says set the value of count to be what was in count before plus 1. So add 1 to count. Increment count by 1. Yeah. Does set bang require the variable to exist already? Yes. So there has to be an instance vars or something like that that creates it. You can set bang an instantiation variable. Even though the user gave a value, you don't necessarily have to stick with that value. You can change it in your program, too. And we'll see later that there are things called class variables that you can set bang. And in fact, you can set bang global variables, although that's what we're trying to avoid. It's part of what we're trying to avoid with this whole object-oriented business. Because if it's global, then somebody else might think you still have the old value in it, and different pieces of your program mess each other up. Other questions at this point? Oh, yeah. If you set bang something global, is that the same as defining it? Yes. Technically, you shouldn't be able to redefine something. That should be an error. Scheme lets you do it, and what it really does is a set bang. Yeah. But one of the properties of interactive languages, as opposed to the kind where you write your program in a file and then hit some button that says compile it, is that you sort of change your mind in the middle because of the debugging process. So Scheme tries to accommodate that, even though ideally you would only have one define creating a variable. Yeah? Do you have to worry about garbage collection? No, that's the whole point of garbage collection. It happens under the rug. The question he's asking is, do we have to worry about what happens to the storage taken up by the previous value of count? Suppose we had not a number in here, but a huge long list of things, and now we set bang it to some different huge long list of things. What happens to the space? So people are going to ask questions like that question a lot during the semester, and they all have the same answer. So here it is. In principle, every datum created during the running of a Scheme program lives forever. Nothing ever goes away. That's the rule. That's the semantics of the language. And there's an infinite amount of memory. In practice, the program that implements Scheme, the interpreter or the compiler or whatever, is allowed to reuse some chunk of memory if it can prove that nothing points to it. That process, finding things that nothing points to and reclaiming the space, that's called garbage collection. And it's certainly one of the top 5 advances in programming ever since you used to program by wiring wires. It used to be, so those of you who've programmed in C or C++ or something will remember this. It used to be that programmers were responsible for saying explicitly, okay, I'm finished with this chunk of memory. You can erase it now. Unfortunately, human beings are really, really bad at that. And they always got it wrong. And they always said, okay, I'm done with this chunk of memory, when they really weren't. Computers are very good at it. Computers are great at logic, at sort of working through the implications of things. And they can figure out whether or not you're through with a piece of memory. And so it's the computer's job to handle all that. And human beings aren't allowed. No people inside this room. So that's garbage collection. Okay, moving on. This is going slowly because people are asking interesting but side questions. So here's a doubler. So define DD, instantiate doubler. Ask DD, quote, say hello. Or hello. And it says, hello, hello. The only purpose of this example is to show you that methods can take arguments. So in the method clause that you see up near the top of the screen, it doesn't just say method, open paren, say, close paren. It says method, say, stuff. And just as in defining a procedure, the first one names the method. So it says what message should correspond to this method. The second one, and any additional ones that there might be, are formal parameters of the method. And when you call instantiate, you always say instantiate, when you say ask, I'm losing my mind. You say ask, it always takes at least two arguments. The first one is an object, not the name of the object, the object. The second one is a word, which is the message you want to send. And then any additional ones are arguments to the method, and they have to match up in terms of how many there are. And before you ask, yes, you can write methods that take variable numbers of arguments with the same dot notation you can use for procedures, regular procedures. So that's it. We can give arguments to methods. Now, here's a new kind of counter. So I'm going to make new counters. So C1 is now going to be this kind of counter. Ask C1 next. I get 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Now let's ask C2 next. I get 1, 6. So in these funny kind of counters, the first number says, how many times have I nexted this particular counter? The second number says, how many times have I nexted any counter, any member of this class? And how does this work? Well, there's a clause called class vars, which create class variables. A class variable is just like an instance variable, except that instead of each instance having one, the entire class has one. The syntax is the same as for instance vars. So if you look up here, we have an instance variable called count, whose initial value is 0. We have a class variable called total, whose initial value is 0. What does initial value mean? The class variable total, its initial value is calculated and sort of put in the box when we see the defined class. So as soon as I loaded this file that has this defined class in it, we created the class variable total. It's not a global variable. There's no, in the global scheme here at the scheme prompt, there's no variable called total. So I just got an error message by asking for it. but every instance of the class shares access to total. When I say next, we increment total by 1 and we increment count by 1, and then we return list count total. This is still scheme. Every method has to return a value. Even if it's okay, there's going to be a value returned. Namely, the value of the last expression in the body. So let's ask C1 next. So we're back to C1, which was at 6. I'm sorry, which was at 5. Now it's at 6, and the count for everybody is up to 7, because I counted C2 twice. I can, of course, ask C1, quote, count, and it'll tell me its count of 6. I can ask C1 total, and it'll say 7. I can also ask counter. Classes are a kind of object. So you can send certain messages to classes. And I can ask counter total. And get the same result as if I asked one of the instances. What happens if I ask counter count? Is that going to work? No, because bad message to class count. Because it's only the instances that have instance variables. Okay? So by the way the instantiate procedure works is it does a bunch of things, but the main thing that it does is it sends a message instantiate to the class. So that's the main reason why classes accept messages, so they can take the instantiate message. The fact that it has messages for its class variables also is just a little added bonus. Okay. All right, moving on. Oops. Okay, define pH. Instantiate person, quote, Brian. Okay, so this is a person class. It has one instantiation variable, namely name, so I gave it the name Brian. Yeah? Could I have said ask total count? No, total is not an object. Total is a class variable. It's a variable belonging to the class counter. Okay? Okay, so I just made a person whose name is Brian. I'm now going to ask BH, because I can't say ask Brian. Brian is what it thinks its name is, but the variable whose value is this object is BH. So ask BH, quote, say hello. Says hello. How does that work? The say method up here is very trivial. Say stuff just returns stuff. So it's the identity function. More interesting, I can ask BH, quote, ask, quote, study. And it says, would you please study? So how does this work? So here's the body of the ask method. Ask method has a formal parameter stuff. So that was the word study. And this says ask self. So that's another category here. So every object implicitly has an instance variable called self. And the value of that variable is the object. So, for example, just to show that, if I say, what's the value of BH? It's this function, because procedures are represented as objects. If I say ask BH self, oops, no method self? That's interesting. Okay, I take it back. It's not a class variable. It's not an instance variable, but it sure acts like one. I'm going to have to look up how that works. Pretend that didn't happen. I'll come back to it. It's an instance variable. And its value is the object. So I can use it in exactly the way it's used here as the first argument to ask. That's what it's for. I can say ask self, do some other method. So I'm asking self to use the say method. Say takes an argument, and what I'm giving it as argument is sentence, quote, would you please, and whatever my argument was. So if I say, ask BH study, ask BH ask study, it says, would you please study? Sounds like a very roundabout way to do things. Why am I bothering to do ask self? And you'll see the answer to that in just a minute. The other thing people know how to do, I can ask BH greet, no arguments. What? Okay, that went, let's try it again. Ask BH greet. And it did work, as you see, but did something else too. Hello, my name is Brian. And again, if you look at the method up there, it's ask self say, sentence, hello, my name is, and then name, which is not an argument to the greet method. It's an instantiation variable of person. Okay, questions about that? All right. So self is the main thing that we have here and how to use it. And now for the fun part. We'll define PP, instantiate pigger, quote, Porky. So now if I ask PP, quote, say, quote, hello, it says, hello, hey. Or if I give it a sentence, that works too. Ask PP, quote, say, quote, hey, aunt way, ute, old hey, or ye, and hey. So how does this work? It has a method called piggle whose argument has to be a word, which is the standard procedure you know and love to turn a word into Pig Latin. And then it has a say method that says if the argument is a word, then ask self piggle stuff. So if it's a word, just send it on to the piggle method. If it's a sentence, if it's a list, there's a data abstraction violation here. We map lambda word ask self, quote, piggle w stuff. So for each word in the sentence, basically, call piggle on it. So that's what the say method does. Now, notice that those are the only two methods in the definition of pigger. But there's something else. There's another kind of class, parent. So this has to do with inheritance, which is the third of the big features that I told you we needed to do object-oriented programming. The way inheritance works in our system is by the technique of delegation. It's a little different from some other languages. Basically, what that parent clause means, right here, is whenever you instantiate a pigger, make an instance also of the person class. And since person has an instantiation variable, I have to give it a value, which is the same as my own instantiation variable name. So go ahead and make a person. And I'm going to keep that person in a pocket that nobody sees. And if I don't know how to do something, I'll ask my parent. So if I say ask pp, quote, ask, remember what ask does for people. It says, would you please? So study more. It says, udwe uye is play adiste or may. Isn't that cool? And it does this even though there's nothing in the pigger class about responding to an ask message. So what a pigger does, you give it a message, think about the cond, is it the word piggle? No. Is it the word say? No. Else, instead of saying error message, I don't know how to handle this, it says, send that message to my parent, see what happens. Okay? So that's why it's important that back in the person class, when we defined ask and greet, we didn't just return sentence, would you please stuff. We said ask self to say that. So there's a pigger and a person. But the person who's the parent of the pigger is a funny kind of person, because in that person, the special variable self does not refer to the person. It refers to the pigger. So when you have a person that's the parent of a pigger, self is the sort of the real object, the object that a human being asked us to make by calling instantiate. That's what self is. So inside Porky, the pig, there's a person. When you ask Porky to ask something, it hands that message off to the person. The person says, oh yeah, I know how to do that. So I'll make, would you please study more? And then I'll ask myself to say that. But myself is Porky the pigger. And so it does have a say method. Even though it doesn't have an ask method, it does have a say method. And that's the one we use. Okay? So it's as if the whole definition of the person class, we're stuck inside the definition of the pigger class, but certain things are overridden. In this case, the say method, which for person is just return the argument, for a pigger is turn the argument into Pig Latin. So we get udwe uye is play adiste or may. And remember how greet works. If I ask a person like BH, greet, says, hello, my name is Brian. Now, what's going to happen if I ask Porky? That's what happens. Because the Piggle method can't handle Y as a vowel. It thinks the vowels are A, E, I, O, U. And that's the right thing for a word like your, Y-O-U-R, or you. The Pig Latin of your is or ye, with the Y moved to the end, because that Y is a consonant. But in the word my, Y is a vowel, and unfortunately we didn't handle that right. There we go. So that's a problem which we'll have to solve next time. Yeah. Yeah, his question is, in this example, Porky asked its parent person a pack of pickled peppers. No. Porky asked its parent person to please say something and to please ask something. The parent person did have an ask method that said ask self say, and that went right to Porky automatically. If Porky didn't have a say method either, then we'd ask the parent again. So basically, the child wins if the child has a method, otherwise parent, otherwise grandparent, and so on. Because what if person itself had a parent clause in it? So that all works. Yeah. You ask an object to do lambda. If you had a message called lambda, it could do whatever that thing did. You can't put arbitrary expressions as the message in an ask. The only thing you can ask is something for which there's a method defined. And so you can't use any old scheme thing in it. Yes? Good question. I guess you weren't in lab, because this week's lab was about that. Yes, there is. The question was, if you're a child and you do have a method for something, can you nevertheless say to use your parent's method? For example, as part of what you're doing. I want to do what my parent does plus something extra. And there's a thing called usual, which we'll talk about later, that does that, yes. But we're not up to it yet. Yeah? Can you ask an object for its parent? No. I mean, you could obviously put in methods for that, but generally speaking, as far as the outside world is concerned, there's just the one object, which is the child. And it's up to the child how it handles messages. So that's sort of the big picture of object-oriented programming, is the outside world knows about your messages. It doesn't know anything about your methods. Those are your business. But also, what you would get is an object, so it wouldn't look very pretty. You could ask it things, I guess. But you don't want somebody else to ask your parent to do things. You want them to ask you so that you get a chance to, do it differently if that's your specialization. Let's see, what's next in here? Are we at the end? Yes, we're at the end of this file. Okay, so next time we'll do the next file and learn some more features. Thank you.